So we've got one more kind of overview lesson that will compare and contrast Java streams with other interesting technologies, trying to show you that streams didn't just fall off the turnip truck, but in fact are part of a long tradition of processing information that flows through various filters and transformers. And some of these things are things that you most likely have heard of. Some of them you've probably used, depending on your background. And depending on what you do later in life, you may use some of this stuff in other contexts as well. So a stream is basically a sequence of data elements, data items, that are conceptually produced one at a time, although we saw with parallel streams, you can get some parallelism that speeds things up. But the idea is that the data flows through these transformation or filtering stages. And an operation can read items from an input stream one by one and can also write items to an output stream. So that's basically showing this. So an aggregate operation can take its input, do some stuff, produce an output. Likewise, this is just sort of beating a dead horse. Not that we're trying to beat dead horses or kill horses, but you basically are connecting these things together and you're joining them up in a pipeline-like manner. That should sound familiar, especially if you've done a lot of other work in computing over time. And that's because this is an implementation of something known as the pipes and filters pattern. And the pipes and filters pattern has been around forever, but it was documented as a pattern in the book Pattern-Oriented Software Architecture, a System of Patterns, which is volume 1 of a 5-volume set of books on patterns. And I was a co-author on 3 of those books, but not this one. And the pattern, pipes and filters pattern, has an intent that states, divide an application's tasks into multiple self-contained data processing steps, which are basically the filters or the transformers, and then connect these steps together using some kind of intermediate buffering or data mechanism to form a data processing pipeline. And you can read more about a revision of that pattern at this link here. Now, what's interesting about this particular discussion, and this is where you have to be very careful with patterns. There's no question that from a conceptual point of view, a stream in Java does something akin to this, in the sense that you're running data through these filters and you're transforming them in one way or another. Filter here is used more broadly. It means both filter and or transform. What's different in the way that streams works in Java, and this is something that only becomes clear when you look at the implementation, is oftentimes, especially for stateless behaviors, there is no intermediate data buffer. So in this model, you can see we have these pipes that are used to buffer the data as they go from one filter to the next. In Java streams, you get that kind of buffering only if you're dealing with stateful operations, like sorting things, for example. And otherwise, they optimize stuff so there really aren't extra data buffers. So that, of course, would be a variant of the pipes and filters pattern that would be implemented differently, but it still has the same kind of feel to it. Data's flowing through something. So that's why you always have to think carefully about whether the pattern is giving you design guidance, is the pattern giving you implementation guidance, is the pattern giving you more constraints than it really needs. So lots of different interesting points there. We've talked about other stuff that has the same properties as streams conceptually, not in implementation detail, of course. People don't implement Java streams with charcoal and filters that you would do for purifying water and so on. But a water purification system is a nice analogy for this. Another nice analogy, which again is not perfect, but will at least get your head around the right frame of reference, would be a pipeline in a UNIX command shell. And this is something that you may or may not have played with. Windows has a command shell, not quite as cool as most Unix command shells, unless you install things like various tools like Cygwin or other adapters that make Windows look like Unix. Mac also has something very similar, other Linux, of course. And here's a very simple example. This is a little script with a pipeline. You go to the /user/bin directory, which produces a list of all the files. You then use the little vertical bar, which is a pipe symbol. It says redirect that into the stream editor, sed, and you strip out the directory part, so you only have things that are going to be actual files. And then we select everything, and then we pipe that through grep, and we get rid of, or we only accept things that start with Z. So anything starts with Z, we're going to, if it's the first character is Z, we're going to take that. We then take the results of that, we sort it, and then we go ahead and we remove or delete the new line character. So we end up with output that looks like this, depending on your version of Unix. So these are all the programs in user bin that start with Z, sorted. And that's a good example of a pipeline. That is, if you ever do system administration work, people typically write scripts that do this kind of things all the time. As I mentioned before, unlike some Java streams, which support short-circuiting, a filter in a Unix pipeline processes all the contents that it gets. It won't short-circuit typically. And it also buffers in ways that you don't get with some Java streams. Yet another example of streams, which actually has the word streams in it, is the so-called System 5 streams. This was something that was developed by Dennis Ritchie, who was one of the original co-founders of Unix many, many, many years ago, together with Ken Thompson and some other folks like Rob Pike and so on. And he developed a protocol processing framework that ran in the context of the Unix kernel, the System 5 Unix kernel, which was developed at AT&T Bell Labs for many years. And the idea was that data would flow from the user-level processes through the different layers in the stream, and then finally to go out of an underlying network device or file system device or whatnot. And likewise, when data came in, it would do the same thing in reverse. And lots of layered protocol stacks like TCP/IP and so on could potentially be implemented using a streams-like approach. There's also something called Java Reactive Streams, which also uses the word stream and is much more in keeping with our use of the word stream in this context. In fact, it's a variant of Java Streams that implements the Java Reactive Streams spec, which we'll talk about in more detail later towards the latter part of the class with this thing called the flow class, which has a bunch of cool interfaces. And we will talk about streams. You'll get a chance to program with Reactive Streams through Project Reactor, being aware that there's other implementations of it as well, besides just Project Reactor. So that's a quick summary of how Java Streams compares and contrasts with other technologies. The key point to come away from this is that the concept of a stream has been around as a pattern for many years to structure the relationship between processing elements in a pipeline-like manner, irrespective of the implementation details of how that's implemented under the hood.